The Earth's crust varies in thickness from about 4 to 30 miles. It consists of more than a dozen tectonic plates that are in constant motion. This dynamic geology regulates the planet's interior temperature, recycles carbon, mixes chemical elements essential to living organisms, and shapes the continents. Deep within the Earth's interior, the movement of liquid iron generates a protective magnetic field essential to complex life. If our planet was smaller, its magnetic field would be weaker, allowing the solar wind to strip away our atmosphere, slowly transforming the Earth into a dead, barren world much like Mars.
We need an oxygen atmosphere, and the oxygen-nitrogen atmosphere that the Earth has is necessary for complex life.
As seen from space, the Earth's atmosphere glows as a thin blue ribbon of light. Measuring less than 1% of the planet's diameter, it is composed of a mixture of nitrogen, oxygen, and carbon dioxide. As a result, our atmosphere ensures a temperate climate, protection from the sun's radiation, and the correct combination of gases necessary for liquid water and complex life.
For a size of planet like Earth, our moon is big. The current thinking is that if our moon didn't exist, neither would we.
1/4 the size of the Earth, the moon's powerful gravitational pull stabilizes the angle of its axis at a nearly constant 23.5 degrees. This ensures relatively temperate seasonal changes, and the only climate in the solar system mild enough to sustain complex living organisms.
If we find life out there, especially complex or even intelligent life, it will be around a star similar to our own.
We orbit what is known as a spectral type G2 dwarf main sequence star. It is well suited for our needs. If the Sun were less massive, like 90% of the stars in the galaxy, the habitable zone would be smaller. To remain within its boundaries, the Earth would have to be positioned closer to its star. Here, increased gravity would lock our planet's rotation into synchronization with its orbit. While one side of the Earth continually faced the Sun and increased radiation from solar flares, the dark side of the planet would lay shrouded in perpetual cold and ice. It is unlikely complex life could tolerate these drastic extremes in temperature.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, that it has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that it has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
if every element has to be there at the same time. You have to multiply the probabilities, and that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillion. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
While a growing body of scientific evidence may support this hypothesis, does the possibility that our planet is rare within the galaxy imply anything about its significance? Recently, astronomer Donald Brownlee considered this question in the best-selling book Rare Earth: Why Complex Life is Uncommon in the Universe.
There's a general feeling that nature wants to make Earth-like planets, and that naturally that life will evolve on them and naturally evolve to something like us. And yet the conditions, the environmental conditions on a planet that would allow more complex creatures similar to people or plants and animals is very rare. And so we wrote the book Rare Earth to point out that the Earth is actually a rather special place.
Brownlee contends that while relatively simple microbial life may thrive on planets throughout the universe, planets capable of sustaining complex life are exceedingly uncommon.
I think if you talk to the people who do this at a day in, day out business, the biochemists who understand what are the things you need in chemical processes to make life possible, they would all say that biochemistry favors carbon-based. Carbon-based life is really extremely likely to be the chemistry of life elsewhere, simply because the carbon atom has a specific bond structure, the carbon bond, which lends itself to very complicated, intricate structures, rings, long chains, all the things that make up organic chemistry on Earth is not replicated using any other element as a substitute. People talk about silicon life. Very unlikely to happen, unless maybe carbon life built computers and then the computers took over. But in terms of just springing up, the chemistry of carbon is simply unique. And that applies on Alpha Centauri or the most distant quasar. The carbon bond is the carbon bond, and there's no substitute for it in the 92 elements. We know the elements.
Well, the entire universe is highly hostile to life. If you compare all the known places in the universe, none of them compare to Earth. We live in a very special environment that provides what we need, provides air, provides food, stable conditions, so that the Earth is almost like a giant organism where its systems are interacting in a way that allows animals to survive. The real question is, why did this happen? Was it just a matter of luck or not?
Logically, I think you have to ask yourself, what if this convergence of factors didn't come about as the result of simply a cosmic lottery or a mere fluke or luck? But what if it's the result of some larger underlying purpose or design? And if the Earth does exist for a purpose, is there any way that we could tell?
On October the 24th, 1995, a rare natural phenomenon unexpectedly triggered a unique search for an answer.
Oh, look at this guy!
It started with an experience I had in 1995. I went to observe a total eclipse of the sun in India. It was my first and still only total eclipse of the sun. It was a spectacular event. It's just an experience for all the emotions.